Welcome to this presentation on LLM observability with Datadog. In this session, we'll explore what LLM observability really means, why it matters, and the key metrics that help us monitor LLM applications. Then, we'll dive into how to implement observability using Datadog and walk through how it can be used to track, troubleshoot, and improve LLM performance. Observability is the foundation for building reliable and trustworthy applications. And by the end of this presentation, you'll know exactly how to make that happen. Let's get started. Since the rise of powerful models like GPT, Lambda, and Llama, generative AI has become deeply integrated into everything from productivity tools to fraud detection systems. But despite this rapid adoption, running LLMs in production is far more complex than traditional ML systems. The models are massive, their outputs are non deterministic, and their inner workings often function like a black box. This makes troubleshooting slow and difficult. And it's exactly why observability is so crucial to monitor model behavior continuously, ensure security, and maintain precision and reliability at scale. Let's take a closer look at why observability is essential in LLM applications, starting with the common challenges teams face in production. First, there's the issue of hallucinations, where the LLM generates responses that sound believable but are actually false or misleading. This can be especially risky in high stakes domains like healthcare or finance. Then, we have security and privacy concerns. LLMs can unintentionally leak sensitive information, reflect biased outputs due to skewed training data, or even expose user data through generated responses. And finally, there's response variance. The same prompt can yield different responses depending on temperature settings or model behavior, leading to inconsistency and user confusion. Prompt lengths, languages, and formats can vary wildly, making it hard to track what's working and what isn't. This is where LLM observability makes a huge impact. It provides faster issue diagnosis by giving engineers full visibility into what happened during a request, from the prompt input to the API calls made, all the way to the model's output. Observability also boosts security by helping teams detect anomalies, such as unusual access patterns or potential data leaks, in real time. And finally, it enables performance optimization by monitoring key metrics like latency, throughput, and output quality. To build effective observability into LLM applications, we need to track the right metrics, and they generally fall into three main categories. First, we have system performance metrics. Here we have latency, which measures how long the model takes to return a response after receiving input. Throughput, how many requests the model can handle in a given time, especially important under high load. And error rate, which tells us how often the model fails or returns invalid responses, giving a direct signal of system reliability. Next are resource utilization metrics, essential for cost control and scalability. CPU and GPU usage show how much compute power the model is consuming during inference. Memory usage helps with scaling and deployment decisions. Token usage is particularly important when using paid APIs like GPT-4, where cost is tied to how many tokens are processed. Lastly, we have model behavior metrics which help us measure quality and user experience. Some are listed below. Now that we've covered the what and why of LLM observability, let's look at how we're implementing it using Datadog. Datadog is a cloud-based monitoring and analytics platform that provides deep observability across infrastructure, applications, and services. Specifically for LLMs, Datadog offers LLM observability features that give us end-to-end tracing of the entire LLM chain, from prompt inputs and outputs to errors, latency, token usage, and even detailed insights into data retrieval and tool interactions within agentic systems. Setting it up is simple and begins with three key steps. Step 1. Add your API keys and credentials. First, define the Datadog application name. Next, you'll need a Datadog application key, which allows programmatic access to Datadog's APIs. And finally, a Datadog API key. Diving into actual dashboards and data, it's important to understand two fundamental observability concepts: traces and spans. A trace represents the full life cycle of a request in your LLM application. Essentially, it shows all the work done to process a single user input. It begins with a root span, which marks the start and end of the trace. Inside each trace are multiple spans. These are the individual units of work that happen during processing. Think of a span as one step in the journey, whether it's calling the model, retrieving knowledge, or invoking a tool. In Datadog's LLM observability, spans are categorized by kind based on what they represent. LLM spans track actual calls to the language model. Retrieval spans capture when the system pulls data from an external source, like a vector database or search index. Tool spans represent a program or service being called, with the input arguments generated by the LLM itself. Task spans are standalone logic steps that don't rely on external services. Embedding spans record when the model generates vector embeddings. And finally, agent spans describe the behavior of autonomous agents, which often involve nested sequences of LLMs, tools, and tasks. Now, let's look at how to set up LLM tracing directly in code using Datadog's LLM Observability SDK. The main pattern starts with a wrap function, which allows you to configure tracing around your LLM logic. Inside this wrapper, your core application logic runs and spans are automatically created and tracked. To manually annotate a span with extra information, like input data, outputs, or metadata, you can use the annotate method. This is helpful when you want to override or supplement automatic tracing. If you want to log a custom evaluation score to a span, for example, the relevance or helpfulness of a response, you can use the submit evaluation method. This works together with export span to capture the current trace context and attach evaluation data as a new column in Datadog. Together, these functions give you fine-grained control over what gets logged. Here's a quick preview of what the LLM observability dashboard looks like inside Datadog. At the top, you'll notice this data is grouped under a specific application, in this case, a program search application. This helps us isolate and monitor traces for just this use case. Each row here represents a span, which is part of a larger trace. You can see the input query, the LLM's output, and next to that, the evaluation response attached to it, such as relevance or groundedness scores. The third column shows the span kind. In this view, you can see LLM spans for model calls and retrieval spans for fetching supporting data from a knowledge base. To the left, spans with errors are clearly flagged, making it easier to investigate failure points quickly. Overall, this dashboard gives you real-time, trace-level visibility into how your LLM is functioning, what queries are being run, what responses are generated, and how each step performs across different dimensions. In this view, we're using Datadog to filter evaluation scores and focus only on low-performing traces. On the far right, there's a column called Evaluation Score. Here, we can quickly filter for traces with scores below a threshold. For example, less than 0.5 to find responses that may be inaccurate, irrelevant, or unhelpful. This makes it easy to identify weak matches, analyze what went wrong, and iterate on prompts or retrieval logic to improve future results. This chart shows the daily volume of LLM traces logged over time. Each bar represents a day's worth of activity, and when you hover over a bar, it displays the exact trace count for that day. It helps us spot spikes, drops, or anomalies in LLM usage, making it easier to monitor trends, detect issues, and understand system load patterns. To close out, let's look ahead to a new methodology called Event-Driven Development, or EDD. EDD is a systematic approach to designing and improving generative AI applications, where evaluation isn't just a testing step, it's embedded at every stage of the development cycle. Now, why do we need this shift? Traditional test-driven development worked well for deterministic systems, where the same input always gives the same output. But in GenAI, responses can vary with each run. EDD replaces that guesswork with objective, data-driven feedback. It works at both the component level, like scoring a model's output, and at the end-to-end level, helping us judge full system behavior in production, like conditions. It helps teams measure production readiness. Most importantly, it enables a continuous improvement loop. In real-world scenarios like chatbot development, EDD helps assess how the system handles diverse, unpredictable inputs, not just once, but continuously as the system evolves. It's a powerful new mindset for building trustworthy, user-aligned AI, and it's quickly becoming a best practice across the industry.